And we have Peter Richtarik from Chaos University. So Peter is a close collaborator and a good friend, and he was at University of Edinburgh the last 10 years before move to Chaos. He's doing research in stochastic optimization, federated learning, many methods like randomized coordinate descent, stochastic gradient descent, and stochastic Newton methods. Apparently the last 2 years are some of his contributions. And today he will speak about second order methods and randomness. So Peter, feel free to start the talk.
So thank you a lot for having me in your seminar. It's a great pleasure. So at least remotely I can speak to you if I can't actually travel. Today I have some slides prepared on second order methods and randomness. So I'll particularly focus on one paper that we have written last year, at the end of last year, with two students of mine. So the paper is down there, you can see it here. This was a short NeurIPS paper. I'm still working on that, but the theoretical results are all there. This is joint work with my student Dmitry Kovalev. He's a PhD student as of this January. He was a master's student until then. And Kostya Mishenko, who is graduating now. We have presented this poster at the NeurIPS workshop. So in fact, in a nutshell, those of you who think this is way too early, you can just click on this link or try to search for the link, read the poster, and you're done. You don't have to listen for an hour to someone. So this is just, or maybe you can listen to me if you want, and then you can go there for a summary. So I'll be focusing on the problem of finite sum minimization. We have n functions, we average them, and we try to minimize this over d-dimensional vector. So this is a key problem in machine learning, as all of you know. It's an abstraction of a key machine learning problem called empirical risk minimization. So here, D typically, this represents the number of parameters of a machine learning model, and N is the number of training data. So you collect lots of data, you form this empirical risk, and you try to minimize this. So we'll assume throughout, later on, once I get through the introduction, that these functions are going to be strongly convex and smooth. And by that, I would mean Lipschitz-Hessian. So I'm not talking about anything having to do with the non-convex world or non-smooth world. What I'm trying to understand here in this presentation is how randomness and second order information can be combined. And of course, this is an active area of research and has been for a number of years, but for some reason with very few theoretical insights and results. And I'll comment on those during the talk. So this is why I need to focus here on the simplest possible scenario in order to get some insight into the problem. So just combining second order information randomness is difficult enough. I don't want to complicate it by throwing in some more complications. This is something for future research. Very quick examples. These are just two examples to have something in mind. L2 regularized least squares or L2 regularized logistic regression would fit in this framework. You would have strongly convex function because the L2 regularizer, everything is clearly smooth. Good. So the outline of the talk is that I'll talk a little bit about stochastic first order methods very, very quickly and explain on an intuitive level and also with a little bit of some complexity formulas why stochastic first order methods are really good. And at the same time, I want to highlight the limitation of all the first order methods, including the stochastic first order methods. And this limitation is something we'd like to get through and beyond with the idea of second order methods. And then I move to this part 2, beyond first order methods. And then these parts 3, 4, and 5, these are the novel contributions of that paper that I mentioned. So glory implied of stochastic first order methods. So first order methods, and I'll focus really here on randomized ones. They have revolutionized optimization in the last decade or two, depending how you're counting. There's lots of literature. All of you know this. And to very first order, maybe even zero order approximation, there are of two types. You have the big N type, and these would be methods based on stochastic gradient descent. This dates back to Robbins-Monroe many decades ago. And big D, when the dimensionality is the difficulty, and this the randomized decomposition decision strategies there is based on randomized coordinate descent. Again, there's lots of literature with many variants of algorithms, and this dates back, the randomization at least, to about 10 years ago. So here, in these big N or big D regimes, randomization is really important, because randomization enables improvement of the deterministic methods, both in theory and practice. The issue, though, of all of these methods, without any exception, is they all suffer from conditioning issues, and much of the research in SGD types algorithms and randomized coordinate descent type algorithms is on how to tackle the issue of conditioning. So here in this talk, I'm not going to be interested in the big D regime. So think of D as being small. In fact, even D is equal to 1 makes a lot of sense here. So D could be 1, 10,000, something that is reasonable, and N is the difficulty. So I don't know. So there's literature on big D and maybe small N, but I'm not going to talk about this. Maybe I have 1 or 2 slides, just a very quick summary. So stochastic methods roughly are better than the deterministic variants because of the following thing. So what happens is the number of iterations goes up because of the stochasticity, but cost per iteration goes down. And then the question is, what is the trade-off? And this is in favor of the stochastic method. So the increase in the number of iterations is not as big as the savings in the cost per iteration. This is why they're good. And this difference could be very, very huge. So here's a very quick plot of just comparison of gradient descent and SGD. Again, this is part of the introduction. So let's say we have a 2D problem. So D is very small, D is 2, and we have 14 data points, training data points. So this A1 up to A14. Maybe this is just logistic regression, let's say. Well, in this case, it's quadratic, so it'd be rich regression. In each iteration, we look at all these 14 data points, and we take a step. And again, all these 14 points, and we take a step. So this is a batch method. Every time we move, we have to investigate and look at all of these data points. In comparison, when we work with SGD, we can move even after we inspect just one data point. So here we take second, 13th, 4th, 10th, 3rd, and so on and so forth. So by the time we inspect all 14 data points, which is about here, we already are much closer to the solution. So we're here. This is closer than this point. We have investigated, we have looked at every data point roughly once in both of these cases, but here I'm much closer. This is why these randomized methods are better. Okay, so I want to highlight one issue with all the randomized methods, and that they all depend on the conditioning of the problem. And there's been huge literature on strategies for improving dependence on the conditioning, such as all kinds of preconditioning strategies. So one can think of layer, batch, and whatever normalization strategies for neural networks as a sort of preconditioning mechanism. Momentum or acceleration of Polyergo-Nesterov. These are strategies how you reduce the dependence of the algorithm on the condition number. Variance reduction, yet another one. You go from multiplicative, maybe dependence on dimension times condition number to additive one, adaptive step sizes, mini batching, important sampling. All of these are big topics in randomized optimization, and all of them are trying to somehow tackle the issue of conditioning. So to make it a little bit more concrete, let's think of this one slide here. I'm going to summarize some of these first order methods. And mu f in this case is strong convexity constant of function f. LF is the Lipschitz constant of the gradient of f. And I'm going to assume that the function is strongly convex and Lipschitz continuous. Now there's this relationship between these quantities. Gradient descent takes LF divided by mu f times log 1 of epsilon number of iterations. This is the condition number. And the cost of each iteration is n, because we have to look at every single data point. So remember, n was 14 in that previous step. When you throw in acceleration, what is acceleration? The acceleration idea is just let's go to the square root of the condition number instead. but we still have to do ON gradient evaluations in each iteration. So this is the conditioning, and N is full pass over the data. So let's look at some other trick. What does stochastic gradient descent do? It introduces randomness into gradient descent. There's no acceleration here. You can do uniform sampling or importance sampling, and depending on what you do, you get one of these two rates, and both of these rates apply in the setting of overparameterized models. Otherwise, there is 1 over epsilon dependence and not log 1 over epsilon dependence here. So you can see the formula is very similar. There's also condition number of sorts, and the condition number is better in this case of importance sampling than uniform sampling. So importance sampling helps. And this rate, if you look at the max of LFIs, is definitely worse than the rate of gradient descent. So number of iterations increases. Okay, so that's what I mentioned before. And that's because LF is smaller than the average of the LFIs, which is smaller than max of LFI. So that's the reason why this is bigger than this. So number of iterations goes up, but cost per iteration goes down from N to 1. So the whole question is this increase in the number of iterations less than a factor of N? And if it is, then we save. And the answer is it is, because of this inequality here. So max LFI is smaller than N times LF, because in fact, all of these LFIs are smaller than N times LF. So this is why SGD is better than gradient descent. So this is in the case of overparameterized models. Great. So now let's look at another technique, variance reduction. What does variance reduction do? Essentially, one way to think of it, we try to get this kind of a rate, but without this assumption. Okay, so now variance reduction almost does that, but there's this extra cost of additive plus N. The reason for that is because these variance reduced methods, they learn all of these gradients at the optimum, and there's N of them, and in order to learn them, you need at least ON times log 1 over epsilon iterations. That is really the intuitive reason for why this is there. Okay, great. And now you can throw in another trick, acceleration, then you get a rate of this type. So it's similar to the square root here, but of course, there's different condition number. You have max LFI, so it's the same as here, multiplied by N, the square root. So this is the best of all of these before. So these are just some examples of randomized methods with various tricks, and there's of course many more tricks. You can do per coordinate step sizes, you can do all kinds of things, and you get various improvements. But what I want to highlight is there's always this condition number here. May be different, maybe just LF may depend on maximum LFIs or the average of LFIs, or the square root of something like maximum LFI divided by mu, and so on and so forth. But the conditioning will always be there. And this is the curse of all the first order methods. So this is what is bad about them. So in order to do something about this, we need to look beyond first order methods. And in the machine learning community, people have been looking at this for a while, and recently quite a bit. So there has been a workshop, NeurIPS workshop, beyond first order methods. There is an ICML workshop planned for beyond first order methods. So there's interest in these. So let's look at a prototypical second order method. So the simplest of them all, of course, it'd be difficult to implement this for the finite sum problem when N is very big, but this is the simplest of them all, is the Newton's method. And what it does, it takes the current model, xk, and you subtract the Hessian of the entire function. So you need to do computation of all the N Hessians, average them, and then invert the matrix and apply it to the gradient. And this again takes the full pass over all data. What is good about this method? It has local quadratic convergence rate, and it's independent of the condition number. So this is really good. No first order method can match this. But what is bad about it, that it really is very difficult to randomize it. And especially when N is very big. When D is big, if that is the issue, there have been some successful approaches to randomization, but for big N, this has been really resisting attempts at solving this issue. So let's look at the big D regime first, and I really have a couple slides here. I will not really go into any depth whatsoever, but here's some work that we have done in our group on this topic. So here, for instance, in this paper, SDNA, stochastic dual Newton ascent, what we do, the way we handle the big N regime, well, this is actually the only of these papers where we looked at big N regime. We look at the dual problem, and in the dual problem, what happens is the number of data points becomes the dimension, and then essentially we try to think of the big D regime, big dimensional regime in the dual. So we do a Newton type step in a random subspace. And we can show that this method, SDNA, has better properties than any first order method in a certain sense. And that property is that it has superlinear speed up in the mini batch size. So no first order method that I know of has this property. And that means that the number of iterations goes down by at least a factor of 10 if you increase the mini batch size by 10, from 1 to 10 by a factor of 10. So at least, not at most, but at least. So there's already something interesting about going second order. In this work, we had some insights into quasi-Newton matrix inversion rules, and it turns out you can randomize them. As something to do with algorithms for matrix inversion. In fact, this is also something to do with SGD. I don't really have time to go there, but once you realize that these quasi-Newton update rules have something to do with optimization, then you could accelerate them, and you get accelerate quasi-Newton matrix inversion rules. They have not been really suggested, even though there's 60 years of research almost on quasi-Newton methods, but this somehow was discovered only recently. In this work with Philip Hanzeli, Nikita Doikov, and Yuri Nesterov, we looked at subspace type Newton methods. So again, big D, and we have the best current rates for these types of what happened. Okay, well, let's maybe use this break for maybe some questions. This is all introductory. I didn't get to the meat of the talk, but maybe there's some questions.
You mentioned that there has not been that much progress in this area when combining second order information and this stochastic setting. Do you have some intuition as to why that is? What were the challenges?
So first of all, I have to qualify the statement. So there has been progress in the sense of there has been a lot of research, but if we look at the finite sum problem and we try to randomize in an SGD type way, then it just turns out that all the theories always worse than even gradient descent. And I will bring the intuition in just the next few slides that I have. So I have about 2 or 3 slides on that. So I'll address it there. And if that doesn't address your question, then feel free to ask further. So I wanted to stop here with the big T. I didn't want to really go into details of any of these papers. And now I want to explain why. So this is the answer to your question. Why the attempts at handling the big N regime really do not really work in a certain sense. So, and I'll explain that sense. Okay, so the first attempt is this. So let's try to do a second order SGD. That's the first idea one may have. And what does that mean? Well, it means just this. So sample one data point at a time, just like SGD, the simplest SGD without any mini batching, and take a Newton step as opposed to gradient step in this direction. Choose some step size, gamma could be 1, could be something else. So do this, I is chosen from the random. This, however, cannot work. And one of the reasons why this cannot work is that, in fact, there is a class of problems of this type where this Newton type update is exactly equivalent to gradient type update. Exactly. So the stochastic Newton method of this type would be equivalent to stochastic gradient descent of this type. And Nicolas has written some papers on this together with me. And because of this, this method will necessarily also have a rate which depends on the condition number. And that's exactly what we don't want. So what do we want out of a second order method? So one way to think about second order method is as soon as you use some second order derivatives, you have a second order method. Fine. But then I can come up with any method which uses second order derivatives, however good or bad it is, I'll just call this second order method. So no, what I want a method which has the properties of a second order method. What would that mean? So for instance, I want to have very fast local convergence rate, something similar to what Newton method does. So Newton method has a local convergence rate, which is, first of all, independent of the condition number, and it's quadratic, so better than any of these first order methods. So I want something of that type. in the rate. So this cannot work. Here's another attempt. The other attempt is like this. So let's build some matrix HK, which is going to approximate the Hessian, and GK, which is going to approximate the gradient. And we do this with subsampling. And the idea is that this subsample is large enough. So if we have, let me click on the pen here, if this set, SKH, is the set of indices for which we're going to compute the Hessian, is large enough, then this HK matrix will be very close to the Hessian, so this inverse of it will be very close to the inverse Hessian, and the same thing applies here. If this set is large enough, then this approximation will be really good. Okay, so we want this approximation to be very good. So this seems to be very intuitive. It seems to be like the first idea you might have besides the stochastic second order SGD. However, anytime we try to do analysis of this type of a method, what happens is that we need these samples, these sets, to be very, very large. And sometimes, in theory, they're even larger than the number of data points that we have. So, for instance, the state-of-the-art theory would say that the number of samples is something like O of kappa divided by epsilon squared, where epsilon squared is some accuracy target that you have, and this condition number could be very big. And essentially, this is going to be, for all practical purposes, going to be very, very close to n, the number of data points, or it could be even larger. So that this could only work if n is really, really huge, and this kappa is small, and epsilon is not that small. So for some state-of-the-art methods of this type, you can look at this paper of Rusta and Michael Mahoney, published in Mathematical Programming. So this cannot work precisely because these huge samples are really necessary. All the theory is based on seeing this method as essentially inexact Newton method, where the inexactness is probabilistic. So we need this sample to be so large that this is very, very close to the Hessian, and we need this sample to be very large so that this is very, very close to the gradient. And in some of the methods in this paper, the full gradient is needed. So not even approximation, but the full gradient.
Peter,
and that means, yeah.
We have a question in the chat. Tim asks how different can be the sets SKD and SKH in this slide.
So in some of the theory in this paper that I'm referring to, but this is just one of the last papers on this topic, this SGK is even the set of all the data. So for some of the results, this is necessary for this to be the full gradient, which already means you take a full pass, which already means it must have worse per iteration cost than gradient descent. And this has to be very large. So quite often these sets are chosen to be independent and random. In some papers, they're chosen to be the same set, and so on. But in all of these papers, these sets are very large, and that's really the message that I want to get across here. Very, very large. So certainly we're nowhere close to achieving the goal of having something of an SGD type method of this type, where we could work with just computation of a single Hessian and a single stochastic gradient. We're not there. So this method has that property. You can compute just a single Hessian and a single stochastic gradient, but unfortunately, even though it uses second order information, it looks nothing like a second order method in practice and in theory, because it could be equivalent to SGD. So that's the problem. So this is the difficulty, that these natural ideas you might get about how to make Newton's method stochastic, they just fail. Okay, so that's really the difficulty. So I'll pause here in case there's any questions, and then I'll move to the third part. So I pause here at this slide where I want to say, at the moment, there's no stochastic second order method, which uses a small mini-batch size, so anything smaller than something like 1 over epsilon squared, which would have some properties of a Newton method. So for instance, it would have local convergence rate, which is either quadratic or independent of the condition number or something of that type. Something that is clearly unachievable for a first order method. So I'll pause here. And that is the end of the introduction, and then I move on into this part where I'll actually talk about the novel results that we have. So let me pause here.
So Peter, question. So the only way in which you can hope for such a rate is that the variance is going down much faster than what you need for SGD, right? So
that's one way to think of it. Sure.
So then the question is the question that you wrote even possible?
Well, that is one of those reasons why this is a difficult topic. So in fact, the methods that we have here that I'll present, they're not unbiased.
Oh,
so they use bias. So the notion of variance is one thing, but we actually have bias there, and it's important that we have bias. So maybe that partially answers your question.
Yeah. All right. Thanks.
Excuse me.
Go ahead. I cannot see you, but I can only see my slide. But please.
Okay. Could you give some intuition as to when Newton's method is equivalent to SGD?
Yeah, sure. So one way to think of it is this. So so let's say that the Hessian. So this is just informal. Okay. The Hessian could be, in fact, a projection matrix. This happens for problems where each Fi is quadratic. In that case, the Hessian is just independent of x. Okay. And it could be the case on top of it that the Hessian is actually projection matrix. And it could be even the case that also this inverse Hessian is a projection matrix. And it also could be the case that this stochastic gradient actually is the eigenvector, which is associated exactly with the eigenvalue 1 of the projection matrix. Projection matrix, they have only eigenvalues 0 and 1. And in that case, because this is the eigenvector of this inverse matrix, the product will always be just the stochastic gradient. So this product just happens to be the same thing as if this was not there at all.
Okay.
And this is a perfectly valid finite sum optimization problem, quadratic, and unfortunately, this trick is not going to deal with that issue.
Okay, thanks.
Okay, so I'll continue, but please feel free to interrupt me at any point. So stochastic Newton method. I'll give two constructions. They lead to the same method, but they are motivated differently. In fact, the first construction seems unmotivated. It seems like a trick. And then in the second construction, I'll unpack how one might arrive at that construction in the first place. So here it is, the method on one slide. So what is Newton's method? You take xk, subtract the inverse Hessian, that is this big thing. I'm just really writing down the Hessian as the average of these local or stochastic Hessians. And this is just the full gradient written as the average of all the gradients, okay? And now I choose to write this product in a funny way. So what am I doing? I'm writing this xk as inverse Hessian applied to the Hessian, this is the Hessian, times xk. So you can see that this inverse Hessian times this Hessian cancels out, you could just get xk. So this product just gives us xk, and the rest inverse Hessian applied to this sum averaged over all the i's gives us this term, inverse Hessian applied to the gradient. So at this point, I didn't do anything. I just rewrote classical Newton method in a different way, where it's written as inverse Hessian applied to some vector. Okay, that's all. Nothing really else happened. Now, what I'm going to do, I'm going to use a trick. I'm going to get rid of all these variables xk, and I'm going to say that I will not have a method which only evolves a single vector, but I will have as many iterates, sorry, as many, not iterates, but as many vectors that will need to converge to something as I have data points. Okay, so for every I have my own vector wik. So I replace it in all of these 4 places, okay? So now I made my life much more difficult because I lifted problem from d-dimensional problem, where I'm just looking for one d-dimensional vector xk, to n d-dimensional problem, where I'm looking at n d-dimensional vectors. Okay, so that is, I'm certainly complicating my life here. And now what I'm going to do, in order to define an algorithm, I need to define how these W vectors are going to be updated. Because if I have some W's, this formula just tells me how to get xk plus 1 from the W's, right? But now that I have the new xk plus 1, I need to use it to update the W's. So how do I do it? This is how I do it. So what I do, I sample a random set of examples. This could be any random set. So it could be singleton, in fact. So this could be just single I. And for those sampled points, I'm going to update those variables to xk plus 1. And the rest, I just don't update at all. I'm going to be lazy. Okay. And again, this sk could be any random set. So it could be a singleton, or could be a set of cardinally 2, or it could be, in fact, set of cardinally n. So what happens if this set sk is of cardinally n, which means it contains all data points? Well, then this is not there at all. Okay, this is empty set. So I always update all the w's to xk plus 1. So I'm back in the situation where all the w's, which I allow to be different, cannot possibly be different. And in fact, this will be just the Newton method. Okay, so I hope you see that by choosing sk to be the whole set of all the training data, this new method will become the Newton method. But by choosing sk to be something smaller, and in particular to be singleton, this is not the Newton method anymore. It's something else. It's randomized, and it has at least that property that I wanted to have, and that is that it can compute just a very small number of Hessians and gradients in each iteration. Why is that the case? Well, because if, let's say, sk is a singleton, then all of these n-1 wik stay the same. So all of these Hessians of wiks that we computed before, and all of these gradients evaluated wik, we already computed. So let's say we store them. We don't have to compute them again. And then what we compute is just the Hessian and the gradient at this new point for a single I. So I only look at one data point and compute the Hessian and the gradient with respect to that data point, and that's it. And then I recompute this formula. Of course, I always have to take the inverse of this, but I'm assuming D is small. So if D is 10, 100, whatever, something small enough so that I can actually solve this linear system here, everything is fine.
A question?
Yeah, sure.
This reminds me of SAG, has a similar flavor. Yes. Or am I missing something? Is it fair to think of it as a second order type SAG approach?
So it's almost there. What you said. I would rather say that this is second order MISO, and I will have some slides on that. And in fact, this is the second derivation of the algorithm that I'll talk about. Yeah.
Okay.
And Peter, how you initialize the WIK, the WI0?
So in theory, this could be absolutely anything. So any vectors. All the W is just arbitrary vectors, and this method will have local convergence guarantees for any initialization of these W's. But in practice, well, I don't know what should be better than choosing them all the same. So once you have a good guess for some W, maybe you should just initialize all the WI's zeros to be all the same. But I don't really have some practical insights on good initialization. So I don't know. This should be investigated.
And we have one question in the chat that Adam asking, is a mix of stochastic Newton and randomized coordinate descent this approach?
Well, so not really, because I'm not really updating single coordinates of these x vectors. So in that sense, not, right? Because if when I update some x vector of w, I can update all the entries of it. So it certainly is not randomized coordinates in that sense that I would ever look at the subsample of a d-dimensional vector or a d by d-dimensional Hessian. But there is some relation that I can think of to randomized coordinate descent, but not classical, but to a new variety of so-called variance-reduced coordinate descent methods, which have only been introduced last year. But this is only something at an intuitive level, and I can't quite formalize it right now. So I'm not sure if that answers your question.
So Peter, is it true that the memory for this is ND square? So you're trading off.
Yeah. Yeah, exactly. So this is not a free lunch here. So there's huge memory involved, just like you would have memory with SAG or with MISO, even larger here, because I know not only need to store all of these gradients, okay, but I need to, I don't have to maybe store the gradients. I can store just these W's, but okay, let's say I stored all of these gradients and but I also have to store all of these hashings.
Right.
So yes, there's huge memory requirement, and still I'm kind of trying to ignore all of these practical issues here, and I'm trying to really zoom in on trying to get a method which can sample as little as just one data point, and for that data point, the hashing and gradient, and get a second order type convergence rate, which is clearly better than anything any first order method can achieve. And we succeeded at this. And now that we know this can be done, we can ask more practical questions, such as how to deal with memory, how to maybe do this inversion faster, and these kinds of things. So we ask some of those questions, but not all of them.
So wasn't there like an stochastic Newton SVRG type algorithm by Loizou and these guys at some point?
So there have been lots of methods of this type, but they always have this property that they need huge sample sizes. So either you compute the full gradient in each iteration, or you need a huge subsample of the Hessian, or if you don't, then there's no theory. I know of no single algorithm that has any theoretical guarantees, which would actually which would be better than some first order method, which can sample just one single data point. And not just that, but anything less than 1/epsilon².
Yeah, that's, I think, true, because Loizou and these guys could only prove a linear rate, so they couldn't prove a quadratic rate.
Yes, so if I go, well, linear rate would be good if it was independent of the condition number. But I think, so for instance, this method is a method which clearly can compute just one Hessian and one gradient. And it can be analyzed, at least for quadratics, and one get the linear rate. But the linear rate is no better than SGD applied to the same problem.
Right. Okay.
So, and that is the disappointing news. So it's successful in some sense, but not in the sense that I want it to be successful.
Okay.
Okay. Okay, good. So here's the algorithm again, written more formally. So we start with any iterates. So this answers Nicolas' question of any starting points, and you choose mini batch size, could be anything, even 1. So I want to stress that it's nothing like 1/epsilon². Could be also n, in which case we recover Newton's method. We apply this iteration. I'm a little bit hiding exactly how I compute what. So for instance, I can cheaply maintain this matrix as cost of OD² in each iteration if I choose mini batch size of 1. And then I have to compute the inverse. So let's say that's OD³ and so on. But all of that work is independent of n. Good. So storage and work. This answers some of these questions. We have to, first of all, compute all these n Hessians and n gradients at the beginning, because in the very first step of the algorithm, we need all of these Hessians and all of these gradients. So that's yet another piece of disappointment, but at least it happens just once. Okay, so one pass, we initialize. Maybe there are some tricks how we can bypass this. We didn't really go into investigating, so we just say, okay, we do it. So of course, practically, you can do all kinds of other approaches. You can maybe run just this incrementally and so on, but we wanted to have clean theory, so we're just doing it this way. So there's storage, and the storage is really big because we need n of these Hessians and n gradients. Okay, so clearly developing some SVRG type method rather than SAC type or MISO type with huge storage of this is something that might be interesting. And then in each iteration, we compute tau gradients, tau Hessians, and one inverse. So that's what's going on. And this tau could be 1. So it could be as little work as simply OD, OD² OD³ in one iteration. So essentially just one inverse of one, hopefully small dimensional matrix. Good. So now the second construction of exactly the same method. So the construction will go as follows. So there is a method called MISO, by Julien Mayral from 2013, which can be viewed as, this is not in fact how this was written in this paper, because the MISO paper doesn't, the original MISO paper doesn't really deal with mini batching, but gradient descent can be generalized to a stochastic method called MISO, or the mini batch MISO. And what we try to do, the same thing to Newton method. And then what we get is the stochastic Newton method. So in other words, the stochastic Newton method I just described is to Newton method just the same thing as MISO is to gradient descent. Okay, this is the intuition. So let's write down gradient descent, but in a funny way, so that this connection becomes clear. So we write down gradient descent in this way. So we have average of these model functions, and these model functions are just linearizations of every fi plus this quadratic thing. So obviously everybody can be quickly convinced that by minimizing this, we're just defining gradient descent. So here's a very quick verification. So when you take the average of all of these model functions, what you get is this. Okay, I think I forgot to write down fxk here. So there's a mistake. I should do plus fxk. And then you do argument of this. So you solve this equation and you get the gradient descent step. So this is nothing else, just a funny way of writing down gradient descent as argument of the average of all of these model functions at every I. Now let's look at MISO. So MISO, as I said, was described in this 2013 paper. And later it was discovered from a different point of view and called finito in this work. And these are some of the early VR variance reduced methods for finite sum problems. Not the first ones. The first ones were SAG and SDCA. SVRG followed later, but very early on. It has same theoretical properties, in fact, as SAG and SDCA. It wasn't shown in this paper that it has the same properties. There's some issues with the rate, but in fact, in this paper, we managed to fix some of these theoretical issues and generalize the method to mini batch method and do analysis also in the non-convex setting and so on and so forth. So in fact, we revisited MISO and now it's on equal footing theoretically with the other variance reduced methods. So now that we have that, now that we have a general mini batch version of MISO developed in this paper right here, we can write it down this way. So again, exactly the same formula without any changes for gradient descent, but the change is here, that the model function is no longer what it was before, but it's this. And the only change from gradient descent is that everywhere here, what I had before was xk, okay? It was blue also, okay? It was xk everywhere here, xk, xk here, xk here. So now I allow every function fi to own their own wik. And then these wiks need to evolve somehow, and the way they evolve would be in this way that I just described for the stochastic Newton. Now, this is not exactly how MISO did it. What MISO did is exactly this, but for sk being a singleton. So this is a generalization of MISO to mini batch MISO. Okay, so this is how MISO can be written down. And if sk is really n, then you can see that all the w's that get always updated to xk plus 1. And what you get out of this method is just gradient descent. And now we look at Newton method, and again can be written in the same way. But now the difference is that instead of this linearization here, we also have a quadratic term where we don't have L here, what we had before, so that we have just 1, but instead here we have the Hessian of that function fi. So we get Newton's method. You can very quickly verify that if you minimize this model, you really just get Newton's method. And now what we do, you can already see, we simply do the same thing as here, but we replace every sk by wik. So that's what stochastic Newton method does. So from this point of view, it looks like a very simple idea. That's not the idea how we actually developed this, but it came to us later that we can interpret this way. But nevertheless, it is a valid interpretation. It makes some sense, at least to people who are familiar with MISO as an algorithm. So now this is the stochastic Newton method. Good. So just to summarize, and I'll pause here for any possible questions. All of these 4 methods, gradient descent, MISO, Newton's method, and stochastic Newton, they all look exactly the same. They are of this form. And the only thing that changes is the model that we use for function fi. And for gradient descent and Newton's method, these non-randomized ones, we have always xk, just this blue vector there. And for the stochastic versions, we essentially replace every xk by wik, and every function owns their own wik, and we have the same formula for updating the w's. And there's a difference here. Instead of L prime here, what we get is this for the Newton method. So I'll pause here for any questions, and after that, I'll move to the theory.
I have a quick question.
Sure.
It seems that so far you have not made any assumptions about the behavior of variance. It's related to Sharan's question earlier. In some types of analysis, we say that variance needs to go to 0 near the solution. We're not making that assumption.
No.
Okay.
No, I'm not making any assumptions. So the only assumption that we will have in the theory is that these functions, every single function fi, is strongly convex and has Lipschitz Hessian. That's the only assumption that we're making. But we are going to have only local analysis because we're extending Newton's method. And Newton's method is known not to converge globally. You need some globalization strategies such as skew regularization or damping and so on. And we're not dealing with these. So we are going to have local theory only, just like Newton's method.
I think that in your paper, you do mention a cubic regularization version.
Yes, we do, but not as a globalization strategy. So we still do local analysis of it.
Okay.
Yes. Okay. So here's the theory. This is the main theorem that we have for stochastic Newton. And what does this say? There's certain Lyapunov function which go down at a certain rate. So you can forget now about the right-hand side, but just investigate what this wk plus 1 is. And what it is just the average of the square distance of all of these wik vectors to the optimal solution. And there is only a unique single optimal solution because we assume every fi is strongly convex. So everything is nice this way. So this is the simplest possible Lyapunov error function one can think of once we decide that there will be n different iterate vectors wik. So all of them better converge to x star. So if all of them do, maybe the average is going to, and that's what we're proving here. And what is the right-hand side? Well, right-hand side has tau, which is the mini batch size. And as I said, it could be 1, could be anything between 1 and n. H is just the Lipschitz constant of the Hessian, and mu is just the strong convexity constant. So this is it. And now if you keep staring at this, you will realize that if tau is equal to n, so if this is n, so you do the special case of this will be Newton method, so this is n, this is n, then this 1 minus tau over n part goes. And all that we get is some constant here times wk squared. And wk squared is not going to be random anymore because of this special case. And this recovers precisely the local quadratic rate of Newton's method. Now, if this is not the case, so let me erase something. So if this is not the case, so I go back and I choose general tau, then this term, which I'm going to highlight just in a second once I manage to find the pen here. Here's the pen. So then this term is going to be there. It's not going to be 0. And it gets multiplied by wk. Okay. I mean, ignore this for a while. So this ignore for a while. I mean, it's there, but ignore it. So this means that the method cannot have a better rate than linear rate. Okay, because this is something non-negative. It gets multiplied by something non-negative. So just something that stands in the way. And the rate cannot be better than 1 minus tau over n times wk. Okay, so it'd be a linear rate. But at least it'd be a linear rate which is independent of any condition number because you don't see any condition number here. There's just tau over n. So in fact, a corollary of this is this. If you start close enough with all the w's, then you get this linear rate, local linear rate. And it's 1 minus 3/4 of mini batch size divided by number of data points. And you can notice there's no condition number here whatsoever. As the mini batch size increases, the rate gets better. So you have at least linear speed up in the mini batch size. well, exactly linear speed up in the min image size. So this type of a rate is not achievable by any first order method because it's independent of the condition number. On the other hand, it's local only, which is to be understood because it's an extension of Newton's method. In fact, Newton's method arises as a special case, so one shouldn't expect anything more without any modification. So let me pause here.
But the neighborhood depends on the condition number, which can be arbitrarily small, right? So
yes, of course. So this is we inherit exactly the same behavior of Newton's method. Newton's method has exactly the same property.
Yeah.
So the rate that we recover, the local quadratic rate for Newton's method, is exactly the textbook rate with exactly the same neighborhood under those same conditions. You can analyze Newton's method under some other conditions as well, maybe self-concordance and so on, but we analyze these classical conditions of strong convexity and Lipschitz Hessian, and this is just the same thing that is known.
I see. And if you do self-concordance, does this neighborhood dependence on the condition number go away even in this case?
Well, we didn't do that analysis, and it should go away, I think. Yeah.
I see. Okay. That would be cool.
Yeah. So this is what we get, and I still pause here because after this, I will only go to the cubic regularization and then some experiments, and I think this is really the main result here. So I want to make sure that everybody has a chance to ask questions about this.
Can you share some more insight about the fact that your method is biased? How does that play into things?
Yeah, so we don't follow any type of analysis of stochastic first order methods. Maybe this is also one of the reasons why coming up with something like this was difficult before, because we don't follow the template of we have an unbiased estimate of the gradient or of Newton's step or something of that type. No, we don't. Everything is very, very biased. So if you just look at say this formula right here, right. So we have some strange matrix here, where we always, let's say, change as one of these stochastic Hessians, and we keep the inverse of it and apply it to something like this. So this, for instance, is not an unbiased estimate of the inverse Hessian, or this is not an unbiased estimate of the Hessian, because there's this history of these W's. So moreover, this vector right here, it doesn't look like a good approximation of the gradient. In fact, one way to think of this is that it's a good approximation of the gradient, but at the optimal point, not at the current WIK. So essentially, we get the speed up because we try to approximate the gradient better than the gradient can approximate itself. So we try to approximate the gradient at the optimum rather than at any current iterate. And that's how somehow we get the second order property inside. So we're not following standard template of first order methods. Instead, what we do, we try to follow the template of the proof of the Newton's method. So these intuitions that we have from the analysis of first order methods, they don't quite apply.
All right, thank you.
And what about MISO? MISO is unbiased or is biased method?
Yeah, okay, so that's a good question. Well, depending how you look at it. So it's a similar situation to when you ask about Sarah. So in some sense, it's unbiased, and in some sense, it's biased. MISO. So MISO has this. So if you look, yeah. So MISO can be thought of as unbiased if you look at it the right way. Okay, let me put it that way.
Okay, thank you.
But if you look at it the simplistic way, it doesn't look like there's anything unbiased going on there. But here there's this additional complication of inverse of this very strange matrix. Right. Yeah. So somehow what we want, so this matrix we need it to be of this form, and we need this to be evaluated at exactly the same points where these gradients are evaluated. because then we use the Lipschitz continuity of the Hessian. So this cannot be just any estimate of this type. We need that synchrony there. So that's one thing that is really needed. But in the proof, at some point, what we do, we just upper bound the norm of this matrix by something like 1 over mu, right? Because all of these things are mu strongly convex. So that's what we do at one point. But we cannot replace this matrix by any matrix which has an upper bound in norm of the type 1 over mu, because we also need this, well, we also need this to be synchronized with this, okay, and that. So somehow this precise form of the Hessian approximation, which is pretty much unbiased, is important. Okay, so I go back here. Is there maybe one more question, or should I move on? In fact, I could even stop here. You can tell me, because I see that I'm already outside of my time. So the only thing that I have here is extension, extra to this is extension to cubic regularization, which takes 3 slides or so, and then I have 2 slides on experiments. So there's, but you wouldn't lose much if I dropped it. So I could either stop here or I could continue depending on what you tell me to do.
So I'm sorry, maybe I have a question.
Sure.
So you're talking about the storage requirements, but the gradient part is actually, you don't need to store much, right?
Well, the gradients are subsumed by the storage of the Hessian, so I wouldn't bother.
So
I wouldn't bother with them anyway.
To your update formula.
Yeah, because these gradients are smaller than the Hessians, and I need to store the Hessian, so that's already.
Yes, but the Hessian at any point x.
Yeah.
Well, each Hessian, the right-hand side, like Hessian times the gradient, that's not very hard to store.
Yeah.
It seems that what's really problematic is on the left-hand side, like what you invert.
Yeah. So the most natural way of handling this, that we always maintain this average. So we always maintain this, and whenever we compute the new Hessian, we can either recompute that one subtracted from here and add the new one, and then invert that. So essentially, we don't then have to store everything. So certainly, there's some tricks we can use. For instance, for generalized linear models, you can do better, and so on. You mentioned
exactly. No, I was thinking
in the paper. Yeah. So we have some comments of that type in the paper, but we certainly didn't go and investigate all possible tricks how this could be done. I mean, in the end, there is unlimited literature on all kinds of quasi-Newton methods, and I think many of these tricks could be applied here. Whether this is about the computation of this inverse or storage and so on. So I think much can be done to make these things more practical. But we just stopped at the theoretical result with a few practical insights, and because we think that this is just the beginning of stuff, and we cannot investigate all the things that we would want to in that single work.
What I find interesting is that we had a paper was saying, let's assume you don't do variance reduction, so you don't have access to a finite size data set, and I give you access to the true Hessian. You don't necessarily want to do stochastic Newton, because stochastic Newton will amplify the noise in the direction of h-1, and basically depending on the alignment between your noise matrix and your Hessian, using second order information can blow up the noise in directions you don't want to. So you will win in condition number, but you will lose in noise.
So this is for convex problems?
Yeah.
And where's the stochasticity coming from?
Oh, so you use stochastic gradient. If you use stochastic gradient, then your gradient matrix, your gradient have some covariance.
Yeah.
That tells you first order method in which method.
I understand. Yeah.
This can be bad, but you don't suffer from this problem, I think, because you are in a finite case, and so since the noise goes to 0, you don't really care about this alignment.
Yeah, and it's not just the finite case, but also that we are not even working with full gradients here. If I mean, I didn't write it that way, but if I try to write this as a method where I would see that I'm estimating the Hessian and then the gradient, then I would not even be happy with computing the full gradient and using it there. I really want this decomposed gradient into these WIKs. It's important for the proof to go through. So somehow I need a better estimator of the gradient than I can get from gradient. Yeah. And if we look into the proof, the reasoning really is that we are really trying to approximate the gradient at the optimal point rather than at the current iterate. And that's how we get this Lipschitzness of the Hessian kick in and so on. So somehow there's several departures from standard reasoning, and this is one of them.
Cool, thanks.
So you want to stop me, or do you want to give me like?
I think that it's okay to finish the slides that you have. It's not that much material, so for people who are still here, I think there's interest to see some of the practical.
Okay, so go quickly to the stochastic Newton, because now you've seen the derivation of the method without cubic regularization. The one with cubic regularization is just this. We just add this extra. Okay, this is not drawing, maybe, I don't know why. Let me see. Pen, okay, because I have a razor. So I just add this term here, cubic. So this is just like before. And I add this term here. So in other words, if m is 0, I get the previous method, but if m is not 0, I get a cubically regularized stochastic Newton method. So for this method, and I will not further motivate this, I'll just mention that this is it. We have this rate. This term is just the same as before. This term is the same as before. And now I have a different constant here. So I had the one constant here, now I have a different one. So that's one departure. And here I have a square root, which I didn't have before. And this square root is slowing things down. Okay, because you can see I don't get, even in the case when this is not here, I cannot get local quadratic convergence because I don't get wk to the power of 2, but I get wk to the power of just 3/2. So, so that there's a slowdown of the local rate. In other words, the non-randomized cubically regularized Newton method wouldn't have local quadratic rate, but would have rate which is just between local linear and local quadratic. And the randomized one has a local linear rate, which is also independent of the condition number. So now the Lyapunov function is a little bit different. There are no distances, but there's function suboptimality, and there's some powers around there. So these are some technicalities that perhaps you can ignore. Tau is the mini-batch size just as before, and h and mu have exactly the same meaning as before. And now if you look at the corollary, we have a similar corollary which says that locally you get a local linear rate, and it's almost the same as before, except of 3/4 we get 1/2 here. Okay, so that's essentially the same local linear rate. Good, so we have that, and then I have just 2 slides on experiments. Here's one. This is the optimistic one, the good one. So where we run the stochastic cubic Newton on some essentially toy problem, because what we work with is L2 regularized logistic regression. Of course, we need to stick to the assumptions. We don't want to test this method on beyond the problems that we analyze. So we do a data set which has 22,000 examples and very small dimension. And remember, we kind of need this because we're inverting matrices of these types and so on. So this is the regime we need to be for this method. D is relatively small compared to n. But notice that here the regularized is very small. It's not 1/n, it's 1/100n, and here it's 1/10,000n. So the strong convexity constant of this thing is very, very tiny, almost non-existent. So you wouldn't expect any first order method to do well either on this or on that. But second order method doesn't worry about the condition number. You have seen that the local rate is independent of the condition number, and we see this. So there's no issue whatsoever. The rate is very, very fast, and it's better than the cubic method without any stochasticity. And here we, just for simplicity, what we did, we partitioned the data set into 10 equally sized parts, and we put those, each partition, we just said that's a new function. So essentially we have a finite sum problem where you have just 10 sums, 10 summons, and we sample one of them uniformly at random. So this is what I believe, if I remember well, we have done. So of course, maybe more fine-tuning could be done to get maybe more out of this, but we're already happy that we're beating the cubic method. And again, I want to stress that first-order methods cannot possibly behave like this on ill-conditioned problems. Even when an acceleration is added or any Adam-type trick which uses per coordinate step sizes or momentum, none of that can handle the situation. One really has to use something second order. And here we apply the stochastic Newton without cubic regularization. And here our experiments show that the method is actually worse than Newton's method on these examples that we tried. Not much worse. I mean, as much worse as maybe our method was better than the cubic Newton here. So you can see our method is here and here. So it's worse. But the rate again does not really depend much on the condition number. So here we chose a zero regularizer, and you can see that the rate is very quick, linear, independent of the condition number. So this is very encouraging. So we believe that one shouldn't be disappointed looking at these rates and comparing to Newton and suggesting that it's slower than Newton. Well, we know it should be because Newton should have local quadratic rate and we only have local linear rate. So we should really be competing with Newton in regimes where Newton is really not applicable, and we didn't really try to do that here. So we really try to compare with Newton directly. So this is it. And well, I actually had 3 slides about cos, but I don't have to go that far. Maybe I just show you where cos is. So this is all that you should know. So this is where cos is, and this is how cos looks like, and this is the group that we have over there. Okay, thank you very much.
Thank you, Peter. So is there anybody with a final question?
Yes. I have one more question. I think that first of all, thank you for your talk. It was super clear, very, very nicely laid out.
My pleasure. Thanks for having me.
I think that the 2 Lyapunov functions that you used for your 2 theorems were slightly different. I think one of them uses suboptimality and one of them uses distance from the minimum. And I'm not very experienced in that, in Lyapunov functions. I'm curious, where does that difference come from?
Yeah. So first of all, it's a little bit hard to even call this Lyapunov function. Usually, I would call something Lyapunov function when it's composed more than one thing. And this is just a philosophical question whether you think of this as just one thing or whether this is average of n things. Once you think of it as average of n things, then you can call it Lyapunov function. Normally, you show rates in optimization for, let's say, distance to the optimum or fxk minus fx star, okay, but not something more complicated. And once this is a combination of a distance and function value or a combination of more things, we just call it Lyapunov function. Okay, I know this is not what you asked. So what you ask is why we look at distances here and function values there. This really comes from the proof techniques that are used. So classical rate for Newton's method actually works with distances because the analysis is of a fixed point type. So once you look into classical textbook of Newton's method, one starts with the distance right away and tries to show that the distance is upper bounded by some constant times the distance squared. Okay, so distance without square is upper bounded by constant times distance squared. And that means that if you are close enough to the solution, then actually local quadratic rate kicks in. So we're trying to follow that analysis for Newton, and there was no need to go into any function values and so on. Of course, we can get rate for function values for free once we have this because of strong convexity. But here we couldn't go directly with the cubic regularization. The techniques, the classical techniques are not really based on distances, but on function values. So we try to follow those. So somehow it turns out that it comes from the proof. On the other hand, again, we have strong convexity and then function suboptimality and distances, they're kind of interchangeable. So I wouldn't put too much attention on that. Once we go beyond strong convexity, maybe this will become really important.
And what is the benefit of having the cubic regularization in the first place? Even in the deterministic case, what's the benefit of having?
So in the deterministic case, cubic regularization fixes Newton's method in the sense that it makes it globally convergent. So Newton's method is not globally convergent, and one of the reasons why it's not locally convergent is this. It's not because it's in some sense is a heuristic. So when you replace your function by this function, so let's say there's just one I, okay? There's no many i's, okay? Just one sum function. So you replace your function by this model and you minimize, and that's your Newton step, and you just keep doing it. Then this approximation is neither upper bound, not a lower bound, it's just an approximation. But in optimization, you usually try to follow the majorization minimization principle, that everything is an upper bound and you minimize an upper bound. But Newton method doesn't follow that principle, and that's why it fails, loosely speaking. But once you do the cubic regularization, once you add here large enough multiple of this cubic term, then if the multiple is large enough, you can actually show this is an upper bound. So you then follow the majorization minimization principle, and then the proof techniques, you have more tools at your disposal to prove stuff, and then in fact this will become globally convergent. So cubic regularization is a fix of Newton's method, which was not really developed from some good kind of algorithmic design principles, and it fixes it, makes it globally convergent. But here we still focused on local theory, so we really focus on what are the properties of cubic regularization locally. And what we realized here, that locally what happens is that you still get better rates, even without the randomization, than some first order method, but it's not a quadratic rate, but it's exactly between linear and quadratic rate because of this power 1/2 times power 1.
I see. But
so it even still does something,
in the stochastic case, though, you don't obtain global conversion similar to the deterministic case, correct?
No, we didn't focus on global convergence rate on purpose at all in this work. We focused fully on the local rates. So the global stuff is future work.
Okay. So if we don't have any other questions, let's thanks Peter again for the excellent talk.
Oh, thank you very much.
All right.